Gostaria de apresentar o professor Stefan Roiser, do CERN, que vai nos falar sobre a questão de transmissão de informação. Eu vou passar a apresentação mais técnica para o Renato, que tem um inglês mais fluente que o meu, certamente, e que o Stefan vai entender a apresentação. Então, é importante para o convidado saber o que estão falando dele, né? E a gente entende também o inglês. Então, queria agradecer a presença de todos e passar para o Renato.
Obrigado, professor. Boa tarde, meu nome é Renato Santana, estamos tendo o prazer... Okay, in English, yeah? Okay, my name is Renato Santana. I'm sorry, this is not nice. At least you have to understand what we are talking about, you. We have the pleasure to have the visit, of Stefan Roiser. He's from CERN, he works there, and he has been working at CERN for 15 years already, and he started with IT. He's not a physicist, and careful with the questions, please, physicists, and he has been working with IT for a long time. His PhD was at Vienna. He's from Vienna. And he has been working with LHCb for 8 years, maybe 8 years, with LHCb, which is one of the experiments at CERN in IT. I mean, today he's the team project leader for LHCb, computing. Yes, sorry, he's a computing project leader. I never know the name, and he's here at Rio also to give us this nice talk, and also I was asked to talk a little bit about another collaboration that we're starting up with LNCC, where the biggest computer HPC of Latin America HPC is there, called Santos Dumont. So we're going to have a meeting tomorrow there, and I think that's it. Yeah? Stefan, thank you very much.
Okay. Yes, that's nice. Thank you. Okay. Thanks a lot, Renato, for the very nice introduction. So I wanted to talk to you about data processing at the LHC today. Now, these are the things I wanted to talk to you about. So the first thing is a very, very quick introduction to CERN, what it is about. And then I would like to take you through the data processing chain from the collider until the physicists can analyze the data. And then I would also like, towards the end of the presentation, to give a bit of an outlook. We're heading in 2021. There is the next run, as we call it. I will explain during the talk what it is, where we have major upgrades of software and computing infrastructure, and I would like to introduce a bit to this. So this is, I try to talk in general concepts, but everything that you see in numbers is something that you get from LHCb. As I'm a member of LHCb collaboration, these are the numbers I can give you. Okay, so before we start, I wanted to show you 4 minutes movie, which I found when I was preparing the presentation, which is from 1974, about data processing at the LHC, at CERN, what it was about at the time. This works. Yes. We turn up the volume.
Hello. In this film, we're going to try and show you what data communications is about and its importance to the physicists, computer users at CERN. Here is a map of the CERN site. It occupies an area of nearly 6 square kilometers.
This is just to show you how big.
And a Medica will now introduce you to the independent CERN-developed network. Before this, we can point out that it is not absolutely necessary to send data via links. Some still prefer the good old bicycle online, but as you will see, certain hazards remain with this technique.
In 1964, an experiment was connected to the Brandy Mercury computer. This link was 1 kilometer long. Since then, the need for experimental computing has increased constantly.
This is the false floor under the computer center. Remember the tiles. Switchboards.
The data acquisition computers, which are connected on the network, are linked to the 6600 via the focus access system, of which you see the front-end communication concentrator here. Let us go now to such a data acquisition computer. This is an experiment at the intersecting storage ring, ISR. CERN experimental area at the ISR intersection 2. A medium-sized computer, an IBM 1800, is used for process control of the experiment. In addition, a link exists to the large Centro CDC 6600 computer. This link is used for online analyses which require larger amounts of computing power than the IBM 1800 provides. It operates while the experiment is in progress by sending data down the link, performing the analysis, and receiving back the results.
When I think back on all the crap I learned in high school,
But
it's a wonder I can think at all. And when
the whole movie is 18 minutes, so I just cut out the scenes. But remember the concepts which were presented there. I'll come back to this towards the end of the
gives the nights bright hush, gives the breeze of summers, makes you think all the words of a sunny day.
Okay, so this was just to introduce you to the concepts of data processing some 30 years ago, or 40 years ago. Now I have one more slide for you, just for your amusement. This was the refurbishing of the computer center. I said remember the tiles; they are still the same in 2005, and they were removing in 2005 some 100 kilometers of cables from these false floors, which were put on and on into the false floors, including a modem from 1970s, which was still in operation at the time. Okay, so let's go a bit towards CERN. So what you can see here is a map of CERN and the LHC. As you can see, this is on the border between Switzerland and France. And what we're operating at the moment is the LHC, which is our strongest accelerator. And this is a 27-kilometer long tunnel, around 100 meters underground, and we're accelerating bunches of particles in clockwise and anti-clockwise, and we're colliding them in 4 interaction points where we have installed these experiments in caverns, and we are recording these collisions in these points. Now, I got a few nice movies from IT about to illustrate how this data processing chain works. Now, this is the first one of those, and we are zooming in again into Switzerland and CERN, and you see it's between. Here's the ring, which is between the Lake Geneva and the Jura, and you can see then these bunches of particles which are traveling clockwise and anti-clockwise in this ring. So there are, in each of these directions, there are not these few, but this 2,500 of these bunches which are traveling into each direction, and we are recording then the collisions of these bunches in these 4 experiments at a rate of 40 megahertz. So every 25 nanoseconds, you have a collision of these particles. And then we are zooming in now into one of the detectors. This is Atlas, the biggest experiment in size of the LHC. And you can see then from these 2 initial collisions of the 2 particles, or these bunches of particles, the new particles emerge, and they are traveling through the detector, and then they are recorded. Now, this is a collision. As you could see before in Atlas, the collisions were at the very center of the experiment. This is a collision of LHCb. This looks a bit different. The shape of LHCb is a bit different than the other experiments, because the initial interaction of the initial collision of the particles are at one end of the detector, and then we are measuring into one direction only the collisions to a very high precision. Now, this is another picture of LHCb as it looks in the cavern with its installation, and here you can see a sketch of the detector, and you can see very nicely here also the different subdetectors, as we call them, and they are responsible for recording and stopping and measuring different kinds of particles. For example, here we have the Vertex Locator, so this measures at a very high precision the initial interaction of the particles. You have a magnetic field, which particles which interact with a magnetic field then bend into a certain direction. Calorimeters, which are stopping certain particles. Muon stations, rich stations in between. So these are the different particles, and the different subdetectors, and each of them is giving information out of the after each of the collisions. Now, if we make the calculation, we have 40 megahertz of collision rate. With, let's say, we have an event size of 50 kilobyte, and we are running per year. We are running 5 million seconds a year the collisions. So if you multiply these 3 numbers, you get to a data size of 10 exabyte of data, which would come out of the detector. Now, there are two things with this number. One is, at CERN we have a lot of storage, but not this size. And the second one is that we don't need all the information that comes out of the detector. And we are doing we are selecting the collisions which are interesting for the physicists in different stages. And this is what I can show you here. So this is, again, we are zooming into one of the detectors. It's again Atlas, and then we are selecting the collisions which are the interesting ones. So you can see that each of these collisions is providing a data packet, and then this goes in a first stage. It goes into what we call a hardware trigger, level 0 hardware trigger, and this makes a very coarse selection of the events. For example, for LHCb, this brings down the event rate from 40 megahertz to 1 megahertz. And then in the second stage, there's a software trigger, which is a computing farm which is also installed in the pit. For LHCb, these are some 25,000 computing cores, and they have a time budget of 35 milliseconds to further bring down the event rate. And what in the end ends up out of the pit is an event. We're going down from 40 megahertz to some 12.5 kilohertz at the moment in run 2 in the current data taking. Now this is another sketch of this trigger from the initial collisions in the LHC. You have the hardware trigger, and then actually this blob here is the software trigger, which is a bit more complicated than only one stage of software triggering at the moment, because we have split this into 2 parts. So this means that we are doing a first part of the software triggering. We're outputting the data onto disk. We're doing some calibration and alignment of the detector to see where the detector stands in space, gas pressures, and so on. And then we're doing a second part of the triggering. And the nice thing about this is that this part of the trigger then can produce already data which the physicists can analyze right away. So part of this information which comes out of the HLT is already right away analyzable by the physicists. I'll come to this again later in the talk. Okay, so if you remember the initial movie, the network speed at that time was 750 kilobit. Now, it's not very much different what we're doing now. We are exporting the data from the experiments into the CERN computer center in the first step. Now, it's just that the throughput has changed. We're exporting something like 600 megabytes a second at the moment. We will be doing more in 2021. We'll go to gigabytes per second. What you can also see here is this is another plot from LHCb. So as I told you before, we're having this hardware trigger, this software trigger, which is running either is HLT1 and HLT2. Now during data taking, we are running the HLT1 full speed, and we are outputting less data from the pit. Now in the interfill phases, when the beam is dumped and the new beam is prepared, we are also running more of the HLT2, and then we are reaching something like 600 megabytes, 400, 500, 600 megabytes a second of the throughput out of the pit. Now the beauty of this is that we're continuously running the software trigger. These peaks here. This is at the time when we are doing data taking, we are running more of this split software trigger. We are running more HLT1, and we are buffering the data onto the local disk, and we're not outputting the data. So this is the throughput out of the pit into the CERN data center. So in the interfill phases, for example, when you have this plateau here, then we are running more of the HLT2, and we output more of the data. Then we start again. Okay, we're running out of data, but then we take again data. We're running more HLT1 and so on. So we're constantly outputting data from the HLT. So the next stage then we are now in the data center at CERN. So CERN itself provides something like 20%. We have to do some offline data processing after the data has arrived from the pit. CERN is capable of providing something like 20% of the capacities that we need in order to process the data. Now, what we have been doing traditionally in the past is that we have been doing a first pass of this reconstruction of the data at CERN, and then the remaining on the grid. Now this has also a bit changed in the meantime, because we're also doing this first pass processing on all the tier 1 grid sites. But what you can see here in the movie is still this old way of processing. And also we are keeping one copy of the raw data. We are always keeping on tape systems at CERN, and we have another copy of the raw data which is going to another tier 1 center, which is providing also tape systems. So this is a sketch of this offline processing as we are doing it, what we call the WLCG grid. So you have this is organized in so-called tier levels. So we have the tier 0, which is CERN, I just explained, and then in many countries we have so-called tier 1 centers, which are big computing centers, which have tape systems, huge disk arrays. Computing power, and then a lot of tier 2 centers around, which are helping also with the data processing for this offline processing. Now, LHCb is also using. Traditionally, this data processing was only done at CERN and the tier 1s. In LHCb, we are also using a selected number of the tier 2 centers for this data processing. And you can see here, for example, in 2016, there was CBPF was one of the sites, which was also one of these helper centers to do the data processing. So the site would usually get the input data from a tier 1 center, process the data, and upload again to the same tier 1 center where the data came from. Okay, so I was asked also to talk about the big data. So this is my big data slide. So this, how much is it? How much raw data are we producing per year? So this is just in comparison to other big players in the computing world. So this is a slide from this is a picture from 2013, and there at that time the LHC was producing raw data 15 petabyte for all the LHC experiments per year. Only the raw data which was exported. Now you can see, of course, there are other players, Google, Facebook, which are producing much more data. On the left side, you can see a plot of the LHCb raw data over the different years, and you can see that 2016, for example, was a very successful year. This is the top bar here, where we had enormous amount of data, because the LHC was producing very good and had very long fills and very good quality of the data. So we were able to extract a lot of data, and we are expecting this to happen again now in 2017. Okay, so this is just a sketch again what I just explained in this first part of the presentation. So we have all the stages in the online. From the bunch processing, hardware trigger, software trigger, and then we're going into this offline processing. These are all this is organized activities. So these are central teams which are helping, which are doing all these kinds of productions. And then at the end of the chain, so to say, is the physicist who can do the analysis or is selecting further the data and can do his analysis on this data. Okay, so just to give this, just to put this a bit in comparison to other activities on the grid. So this WLCG grid that I showed you. So this is this is the CPU work that we spent on different activities in 2016. Okay, so this purple and this dark blue is the data processing. So this is what I just explained. The one above is all the user activities, and the big green part here is the Monte Carlo simulation. So basically, the distributed computing that we need, and what also CBPF, for example, is helping for, is the Monte Carlo simulation, where we're spending 85% of the work in this area. Okay, so let's look a bit into the future. So now the LHC is organized in so-called runs. So we had 2010, 11, and 12. We had the run 1. 15, 16, 17, 18. We are now in run 2. We are in 19, 20. There's a shutdown period where we are reorganizing ourselves, and then in 2021 there's a big step for LHCb where we are going into run 3, where we are reorganizing the data processing chain. And I wanted to show you a bit what we are changing now in the future, and to explain a bit to you where the software and computing is going. So this is just a slide from run 1. I will skip this. This is the current data processing as we're doing it in run 2. I've explained to you already this online processing through the different trigger stages, and then we're outputting this 12.5 kilohertz that I told you before. We are outputting 2 different streams at the moment, as we call it. One is the full stream, where we again reconstruct the data, and then we are doing some stripping where we do further selections and streaming of the data into different channels for the physicist. And then there's a new concept that we have introduced now in run 2, which is called the turbo data. Now this is because we have reorganized the HLT, that we can output already fully reconstructed events. We just do a little bit of reformatting on the grid, and the data is analyzable right away by the physicists for this data. Now, what will change in run 3? If you compare these 2 pages, so one thing that you may have noticed is here in the online part, we are not having a hardware trigger anymore. Okay? So that means that the full event rate that we're getting out of the LHC, we will be triggering only in software. So this will produce a huge strain on the software, because we have to improve the performance of the software by several orders of magnitude. And then the other thing that you will notice here is the full stream has disappeared. So we are aiming at only outputting this turbo data anymore on the grid. So this means also the turbo data is smaller than the full stream data. So this means that we have many more events that we will output will make available to the physicists. And so this will put another strains in many different areas of the computing. Also, what happens is that with the grid, you may think that the grid will be idle, but actually what we will be doing is, because we have the Monte Carlo simulation scales with the number of events, signal events that we're outputting from the experiments. So the simulation work that we will have to execute on the grid will explode dramatically. So we have to also invest a lot into this area. Okay, so this is just a sketch just to show how the triggering is done in the good old times. So this means that we are trying to find the needle in the haystack to the signal events that are useful for the physicists. And in run 3, what we're expecting is a pile of needles, and we will be just streaming the data just to give the right quantities to the physicists in different streams. But all this has to be organized, of course, in different ways. Okay, so this is just a wrap up of probably what I just said. So we'll trigger in software this final calibration alignment I just said or just explained before. So this is what we're doing already in run 2, and we will keep on doing in run 3. Turbo stream, and then so the smaller event size produces a lot of more signal events for the physicists. Okay, so now the software, we have to improve the software. That's clear. Now there is hope. This is a plot that was shown 2 years ago in a computing workshop, and the title is Moore versus Moore. So Moore is our trigger software, and Moore's law, you know the Moore's law of every 18 months doubling the number of transistors. Now this is how the performance of the farm evolved over the years, and these are the number of trigger decisions that we were able to take. Now you see that we are branching off here, and we are not able to keep on we're not able to keep the pace of the hardware that what the hardware in principle would provide us. So now we have to reorganize the software, and what we are doing is we are rewriting the software framework. In the software framework that we're using is 15 years old. This was at the time when we had single-threaded computers, and we were just updating to the next version of the computer with a different clock speed, and we were gaining. Now, in a multi-core environment, we have to do different things. So we are going into, first of all, into an area where we are going into multi-threading of the framework, and what we're also highly investing into is the vectorization capabilities of the CPUs, so that we have a single SIMD instruction, so single instruction, multiple data, so that we can produce more throughput in the trigger. So this is all work which is currently ongoing. Another plot to motivate why we need more and better software is the simulation. I told you already that we expect the simulation work to explode because of the number of signal events. Now this is a plot which was shown by our simulation group. So this is the dotted line that you can see here is the pledged resources. So this is WSCG every year gives us a certain amount of CPU which we're allowed to use to process our data. And if we extrapolate this into 2021, 2020, we are at this line. Now, if we look at the simulation work that we will need, if we are currently, if we continue what we are doing now, we are off by several orders of magnitude. So what we need to do is, in order to get back on track, is that we invest into faster simulations, and we do, with less work, we do the same amount of data. Okay, so this is our timeline for the computing project. So we are in 2007, in the middle of 2017. So there's a technical design report which we are producing right now, which we have to submit by the end of this year, and then next year we have to produce another document where we describe the computing model, how we organize our data, and processing in the data processing chain. So this is just to tell you how we organize the work of the computing project itself towards this upgrade. So we have split this into two parts. So the first part, which we call the revolutionary part, is everything that is software engineering, that we need to re-engineer the data processing framework. The event model has to be reorganized, which is storing all the data. Some parts of We have a detector description mode system where we are describing the detector, which is 15 years old, conditions data. All this has to be redone in order to get the most out of the processing. And then there is a second part of this upgrade work, which we call the evolution. So this is more things that come as we go along in our work. Yes, please.
Just a question. Underlying it is Jean. This is what you're talking about?
Sorry?
Underlying it, the simulation is Jean?
Yes, well, there is Géant is the Géant 4 at the moment, is our detector response simulation system. But we have around this we have a framework which we call Gaudi, and Gauss, which is our simulation framework, which is taking the generator data, giving it to Géant 4, receiving the output, storing it, and then we do the remaining chain of the data. Yes. Okay. So then I'm coming already to the end of the presentation, but this is something which is very dear to my heart. I think it's very important because we have to. The computing project is not doing all this work alone. Okay, we are writing the core framework. We are rewriting the core framework, but then all the algorithms and the reconstruction and the trigger and everything needs to be done by the physics subgroups, and they need to adapt the software to this to the new ways of working. And C++, for example, has evolved a lot in the last years. So we're going into new standard now. There's a new Python coming, and so on. So we need to invest a lot into the training of the experiment. And the way how we are organizing ourselves is first that we're organizing courses for the physicists. So this is something during there were some 50 people attending both in the room and remote. That's very nice. And the second part is we are doing hackathons where we have 1 week where we only concentrate on the upgrade of the software, and we get the experts, the software engineering experts, and the subdetector and subsystem people around the table and try to progress and push as much as we can in this 1 week. And these hackathons are organized every other month or so. Okay, so now there are even more things that we need to do for the upgrade. I just wanted to flash quickly this slide. So as I said, we need to make sure that the distributed computing framework scales with the amount of data. We have to reorganize our analysis model. At the moment, physicists are this last selection that physicists are doing on the grid. They're submitting individually their jobs to the grid, and they're selecting the data themselves. Now, with this explosion of data, the I/O to select this data will become the bottleneck because you have a very sparse reading of the data. So we are trying to reorganize this analysis and to group this kind of selections in the future. So this is something that we need to do, and I mentioned already the computing model. This is something we need to think about for next year, how to do this. And that's my last slide. Yes.
Thank you very much. Any question?
How much artificial intelligence you are putting up in the evolution and revolution of the coding of the software?
Well, the computing project itself is not too much involved into this. But then, for example, in the trigger, we are running already machine learning algorithms to do this, and we are investing also in the future into this area.
You talked about improving software ideas. Are you counting on harder evolution for 2000
Yes.
21
Yes.
or?
Yes. I mean, there's a natural evolution of the hardware that we are calculating into the budget that we expect in, let's say, 2019 or 2020 when we will install the farm. This will give us part of the gain that we will have, but it will not provide us everything. Okay. But what we are also doing is that we are investing into looking, for example, to run certain parts of the algorithms to run on GPUs, for example, or to port our software to different architectures like ARM or OpenPower, so that we can see where we get the best price per event benefit. I mean, if it happens, yeah. No. No, I mean, we are investing at the moment, we're investing into different areas where we could see possible gains, but then of course you have to see, I mean, if for example, if you go into GPUs, do we have enough data to fill the GPUs in order to use them efficiently? Also, what is the cost of the GPUs versus normal Intel architectures? So this is, but we are developing in different areas. Yes.
You did not mention the network technologies for this next generation computing. The network technologies.
Well, there are two things that. Sorry. Yeah. So the output rate. I mean, there are two things where the network will play a role for the processing chain is the output of the trigger, which we have 2.2 to 5 gigabyte second output rate. This we will manage. And then you're talking about the grid or more about the
those ones that are near of the detector.
In the detector. I'm afraid I cannot give you any details on this. Sorry, that's something to. No, it's not that I don't want, but it's more a question more to the online people. No, there will be no reconstruction stripping. It's just a little bit of this Tesla reformatting of the data.
Hi. Among scientific programming languages, why Python?
Python, I think it's something that is widely known and many people are using, because one thing that you have to take always into account is also you want to get, for example, for the software engineering, you want to attract people to the software engineering efforts. So if we would stay with COBOL, nobody would come to do software engineering for us. So we have to, and this is also, for example, in what I mentioned in the training. I mean, it's very nice that we are. I think it's very nice that we are going to new standards, C++17, Python 3, Git. We had a lot of homegrown software packages, for example, for the build system, for the nightly builds. Now we're going to industry standards, so that means that people who want to contribute to CERN. They build on, they learn about industry standards, and then if they go back to industry, they have learned already these standard ways of doing it. Okay. So, and it's really powerful. Okay. I don't understand why I don't see Scilab out there. I think I presume it's I mean, if you look at the most widely used languages in the world, it's because of this.
Okay.
Hi. What are the expectations for the next few years related to LHCb software stack to integrate the software stack with new technologies like software-defined networking and network functioning, virtualization, something like this.
Well, virtualization, we are investing a lot into running on virtualized infrastructure. So both the infrastructure that we have at CERN in order to operate our distributed computing, for example, is all running on virtual machines. Now, also on the grid, we are investing into we are running actually on cloud infrastructures. So we are interacting with I don't know, you name it, OpenStack, OpenNeighbor, this kind of IaaS infrastructures, and we also have virtual machines which are self-organizing, which is something that LHCb was the initiator of. Is that you run basically only on the hypervisor, you run a virtual machine, and then on a certain cluster, and the virtual machine replicates depending on the demand of the computing, and also shrinks down. So you don't even need to have any IaaS infrastructure. So these are things that we are doing. Software-defined networks is not something that we are really. Network is a bit out of the. I mean, we are a user basically of the network, for example, on the grid. So this is something that the computer centers are organizing, or the end-brands and so on. There was a project in this area to run with FPGAs on regular machines also, yes. But I must admit I cannot give you more details.
I had a funny comment some time ago from the president of INFN, saying that in the future they were considering, instead of installations, big installation, computer installation, just renting services from Amazon Web. Is that the way to the future?
I think the answer to this is whatever works best. I mean, what we will be doing. I mean, what we need at the moment, what we're doing is high throughput computing. So if we can get more data processed via cloud infrastructures and the institutes or the tier ones are renting the infrastructures from cloud providers, this is something that we will be able to use, but this is not in our hands. I mean, for example, CERN is currently investing in, or has already the third project in this area, where they are extending the CERN processing realm by getting cloud infrastructures and putting just an overlay on the cloud and the CERN batch infrastructure and the remote processing site, which we have one in Hungary, to provide a uniform processing environment. So I think it's a matter of how the price is evolving in this area. If it's worse, we are capable of doing it, and we can jump on it right away. We have an example. We had a cloud infrastructure which was provided to us. In 3 days we were running there. So.
Okay. I want to thank you again. Thank you for the exit.